You're standing on the equator, and the ocean beneath your feet is frozen solid. No open water, no blue. Just ice, a kilometre thick, from pole to pole. In 1992, geophysicist Joseph Kirschvink named it Snowball Earth, and tropical glacial deposits proved it was real. Temperatures plunged below -50. Photosynthesis collapsed. The oceans lost their oxygen, and the ice held for 57 million years. How anything survived remained a mystery for decades. Then geologists found the answer, written in ancient carbonates deposited the moment the ice broke. What emerged was a planet that nearly sterilised itself, and may have triggered the rise of all complex life in the process. Tonight, we trace how the freezing began, discover where life clung on, and ask whether it could ever happen again. If this helps you unwind, hitting like and subscribe would mean the world. The ice is waiting. Let's step onto it. To understand how the world froze, you first need to understand the world it froze from. And that world was nothing like this one. Roll the clock back 750 million years. The continents you know do not exist. There is no Atlantic, no Pacific as you would recognise it, no Himalayas, no Andes, no ice caps at the poles. Instead, the land masses of the Earth are fused together into a single vast supercontinent that geologists call Rodinia, a name borrowed from the Russian word for homeland. And Rodinia does not sit where you might expect it. It is not gathered at the poles or scattered across the mid-latitudes. It straddles the equator. Almost all of the dry land on the planet is clustered within the tropics, baking under a sun that, strangely, is dimmer than the one you see today. Roughly 6% dimmer, in fact. The sun in the Neoproterozoic was a younger star, still brightening over the billions of years of its main sequence, and the Earth received less energy from it than it does now. That single fact will matter enormously before this story is over. The atmosphere you would have breathed, if you could have breathed it, was profoundly different from the one outside your window tonight. Oxygen levels were a fraction of what they are now. The precise figures are debated, but most estimates place them well below what any animal you have ever seen would need to survive. Carbon dioxide was present, and so were traces of methane, both greenhouse gases, both helping to keep the surface warm enough for liquid water despite that faint young sun. The balance was delicate. It had held for an almost incomprehensible stretch of time. This is the era scientists sometimes call the boring billion, a name that sounds dismissive but captures something real. From roughly 1.8 billion years ago to around 800 million years ago, the Earth's climate barely moved. The ocean stayed warm. The atmosphere stayed stable. Life existed, but it was overwhelmingly microbial. Cyanobacteria, simple algae, single-celled organisms drifting through shallow seas that had looked more or less the same for a billion years. No animals, no plants on land, no eyes, no limbs, no predators. Just cells replicating in the dark warmth of a planet that seemed to have settled into a permanent, quiet equilibrium. The oceans themselves were nothing like the seas you know. At the surface, cyanobacteria produced small amounts of oxygen through photosynthesis, just as they had for over 1 billion years. But below that thin sunlit layer, the deep ocean was largely anoxic, starved of oxygen, rich in dissolved iron, and chemically hostile to anything that depended on aerobic respiration. If you could have dropped a probe into the deep Neoproterozoic ocean, what you would have found would have resembled the Black Sea today, stratified, stagnant, and dark. This was not an ocean teeming with life. It was an ocean holding its breath. And the land was bare. No soil, no roots, no forests. The continents of Rodinia were expanses of naked rock and sand, scoured by wind and rain, without a single organism visible to the naked eye. What life existed on land was microbial, clinging to the surfaces of rocks in thin biofilms, utterly inconspicuous. The world was functional, it was stable, and it was ancient, but it was waiting. Something was about to change. Something so extreme that it would reshape every system on the planet, from the chemistry of the oceans to the trajectory of life itself. And the first clues that it had happened would not be found for another 700 million years. They were found in the rocks. In the middle of the 19th century, long before anyone had heard of Snowball Earth, geologists began pulling strange things out of Precambrian sedimentary layers. In 1871, a Scottish researcher named J. Thomson reported finding ancient glacial material, tillite, on the island of Islay off the west coast of Scotland. Similar discoveries followed in Australia in 1884 and India in 1887. Then, in 1891, a Norwegian geologist named Hans Reusch described what he interpreted as a glacial moraine at Biggenjaga in the far north of Norway, a deposit of rocks and debris that bore the unmistakable signature of ice. These were not young formations, they were Precambrian, hundreds of millions of years old, and they were turning up in places that did not make obvious sense. The problem was simple but profound. Glaciers leave very specific fingerprints. They scratch parallel grooves into bedrock. They carry boulders and drop them into fine marine sediments. Dropstones, they are called, rocks that have no business being where they are unless something carried them there and released them. They produce thick, chaotic layers of unsorted debris called diamictites, where cobbles and sand and clay are jumbled together in exactly the way a glacier leaves them. These signatures are distinctive. Geologists recognized them easily from the modern world, and they were appearing in ancient rocks on almost every continent. But there was something troubling about the locations. Some of these glacial deposits appeared to have formed not at high latitudes, where you would expect glaciers, but in the tropics. Thick carbonate sequences, the kind of rocks that only form in warm, shallow seas, sandwiched the glacial layers above and below, as if the ice had arrived in the middle of a tropical paradise and then vanished again. It was baffling. It was for a long time easier to ignore than to explain. An Australian geologist named Douglas Mawson spent much of his career studying Neoproterozoic rocks in South Australia, where the glacial sediments were thick and unmistakable. He recognised their extent and speculated that the glaciation might have been global, but Mawson's reasoning was built on a mistaken assumption, that the continents had always been where they are now. When the theory of plate tectonics arrived in the mid-20th century, it seemed to solve the puzzle neatly. The continents move. What looks like tropical glaciation today might simply be glacial deposits that formed at higher latitudes and then drifted into the tropics over hundreds of millions of years. Problem solved. The strange rocks could be explained away, and for a while they were. Then, in 1964, a Cambridge geologist named Brian Harland did something that reopened the question entirely. Harland had been studying glacial rocks in Svalbard and Greenland, and he had paleomagnetic data, measurements of the ancient magnetic field preserved in the rocks at the time they formed. Those measurements told him where the rocks had been when they were deposited. Not where they are now, where they were, and the answer was startling. The glacial tillites in Svalbard and Greenland had formed at tropical latitudes, not near the poles, not at 50 or 60 degrees, in the tropics, close to the equator. Harlan published his findings and argued that an ice age of global extent had occurred near the end of the Proterozoic, a glaciation more severe than anything in the Pleistocene, more extreme than anything the modern Earth has ever experienced. He recognised what many had suspected, but none had been willing to say plainly. The glacial deposits scattered across the world's continents were not isolated, local events. They were the fingerprints of something enormous. The response was cautious. Paleomagnetic data in the 1960s was still a young science, and the measurements were not always easy to trust. The idea that ice had reached the tropics was extraordinary, and extraordinary claims needed extraordinary evidence. Many geologists acknowledged Harlan's data, but stopped short of accepting his conclusion. The idea sat in the literature, respected but unresolved, for nearly 3 decades. No one could prove it wrong, but no one was willing to build on it either. What Harlan could not have known was that the evidence he needed was already forming in a different part of the scientific world, in the laboratories of geochemists, in the magnetic signatures of ancient iron formations, and in the mind of a geophysicist at the California Institute of Technology who was about to give the whole idea a name. In 1989, at a gathering of researchers organised at the University of California, Los Angeles, a geophysicist stood up and presented an idea that most of the room was not ready to hear. His name was Joseph Kirschvink. He worked at the California Institute of Technology, and he had been thinking about a problem that had nagged at geologists for decades: the strange presence of banded iron formations in Neo-Proterozoic rocks. Banded iron formations are ancient sedimentary rocks made of alternating layers of iron-rich minerals and silica. They are among the most distinctive deposits in the geological record, and they tell a very specific chemical story. For iron to accumulate in seawater in the quantities needed to form these layers, the ocean must be anoxic, free of dissolved oxygen. Iron dissolves easily in water that lacks oxygen, building up over time. But the moment that water meets oxygen, the iron oxidizes and precipitates out, falling to the seafloor as rust. Banded iron formations are, in essence, the chemical receipt of an ocean that spent a long time without oxygen and then suddenly received it. Here is what made them strange. Banded iron formations were abundant in the early Earth, when the atmosphere and oceans contained very little free oxygen. They are a signature of the Archean and early Proterozoic. But then, around 1.8 billion years ago, they vanished from the rock record almost entirely. The oceans had gained enough oxygen to keep iron dissolved and precipitated in a steady state, and the conditions for banded iron formation disappeared. For over 1 billion years they were absent. Then, in the Neo-Proterozoic, right alongside those puzzling tropical glacial deposits, they came back. After a 1 billion-year gap, iron was accumulating in the oceans again. Something had stripped the oxygen out of the water. Something had sealed the oceans off from the atmosphere long enough for dissolved iron to build to extraordinary concentrations. Kirschvink saw what this meant. If the entire ocean had been covered by ice, sealed beneath a frozen lid for millions of years, then gas exchange with the atmosphere would have ceased. Oxygen in the water would have been consumed by chemical reactions and biological processes, with no way to replenish it. The ocean would have turned anoxic. Iron would have accumulated. And when the ice finally broke, the sudden exposure to oxygen would have precipitated all that dissolved iron at once, laying down exactly the kind of banded iron formations that geologists were finding in the Neo-Proterozoic record. The ice explained the iron, The iron confirmed the ice, but Kirschvink went further. He asked the question that no one had satisfactorily answered. If the entire planet froze, how did it ever thaw? Ice reflects sunlight. A frozen Earth would bounce most of the sun's energy back into space, locking itself into a permanent deep freeze. The ice albedo feedback that caused the freezing would also prevent the escape. It was a trap with no obvious exit, unless you considered volcanoes. Volcanoes do not care about ice. They erupt regardless of what is happening at the surface, driven by the heat of the Earth's interior. And when they erupt, they release carbon dioxide. Under normal conditions, carbon dioxide is removed from the atmosphere by chemical weathering. Rainwater dissolves the gas, carries it to the oceans, and locks it into carbonate minerals on the seafloor. It is a thermostat, a self-correcting cycle that has regulated the Earth's climate for billions of years. But on a frozen planet, there is no rain. There are no rivers. There is no weathering. The thermostat breaks. Carbon dioxide pours into the atmosphere from volcanoes and has nowhere to go. It accumulates. Year after year, eruption after eruption, for millions of years, the concentration climbs. And eventually, it climbs high enough that even the reflective power of a planet-wide ice sheet cannot hold back the greenhouse warming. The ice begins to melt. And once it starts, the same feedback that locked the planet into its frozen state now works in reverse. Dark ocean absorbs heat, melts more ice, exposes more ocean. The thaw, when it comes, is catastrophic and fast. Kirschvink presented this framework to the research group at UCLA in 1989. 3 years later, in 1992, he published it, not as a landmark paper in a major journal, but as a short contribution buried deep inside a 1,348-page volume on the biology of the Proterozoic. It ran to just 7 paragraphs. He called it Snowball Earth. Think about that for a moment. One of the most radical ideas in the history of Earth science, the proposal that the entire planet had frozen solid, possibly more than once, entered the scientific literature as an unrefereed 7-paragraph article that most researchers never saw. It was a geological classic hiding in plain sight. And for years, almost nobody picked it up. Only 2 other geologists openly supported the idea at the time, C. Klein at the University of New Mexico, and Nick Bukes at the Rand Afrikaans University in South Africa. The 3 of them, and essentially no one else, believed that the Earth had once been a ball of ice. The idea did not die, but it did not catch fire either. It sat in the literature for 6 years, waiting for someone to build the case that Kirschvink's short paper could not. Waiting for someone to take the hypothesis out of the theoretical and into the field. To find the rocks, measure the chemistry, and show the world what Snowball Earth actually looked like in the geological record. That someone was working in Namibia. In the mid-1990s, a geologist at Harvard University had been spending his field seasons in the remote northwest of Namibia, on the edge of what had once been a vanished ocean. His name was Paul Hoffman. He was studying Neoproterozoic sedimentary rocks on the Congo Craton, layers of ancient carbonate and glacial debris that told a story he could not yet fully read. The rocks were extraordinary. Thick sequences of warm water carbonate, limestone and dolomite formed in shallow tropical seas, were interrupted by unmistakable glacial deposits, diamictites, dropstones, striated surfaces, and then, sitting directly on top of the glacial layers, something that had puzzled geologists for decades: cap carbonates. Cap carbonates are thick beds of carbonate rock, sometimes meters to tens of meters thick, that appear immediately above glacial deposits in Neoproterozoic successions all over the world. They are chemically precipitated, not biological in origin. They appear in sequences that otherwise contain no carbonate at all, as if something extraordinary had happened to ocean chemistry in the immediate aftermath of glaciation. They are found on every continent. They are found at every paleolatitude. And they demanded an explanation. Hoffmann saw what Kirschvink's hypothesis predicted. If volcanic carbon dioxide had accumulated to extreme levels during a global glaciation, hundreds of times the modern concentration, then when the ice finally broke, that carbon dioxide would dissolve into the newly exposed ocean. The warm carbon dioxide saturated water would react with the enormous quantities of weathered minerals flushing off the continents in the post-glacial deluge, and calcium carbonate would precipitate rapidly in the surface waters. The cap carbonates were not a mystery. They were a receipt. They were the chemical signature of the most extreme climate reversal in the history of the planet. A swing from total glaciation to a brutal greenhouse in what might have been just a few thousand years. But Hoffmann needed more than rocks. He needed chemistry. Working with a geochemical oceanographer named Daniel Schrag, who had spent years using isotopic variations in coral reefs and deep-sea sediments to reconstruct ancient climates, and with Alan Kaufman from the University of Maryland and Galen Halvorson, Hoffmann measured the carbon isotope ratios in the carbonate rocks bracketing the Namibian glacial deposits. What they found was devastating in its clarity. The ratio of carbon-13 to carbon-12, a proxy for biological productivity in the surface ocean, showed enormous negative excursions. Before the glaciation, biological productivity was normal. During the glaciation, it collapsed. The surface ocean had gone dark. Photosynthesis had effectively ceased for millions of years. This was not a regional event. The isotopic signatures matched patterns found in Neoproterozoic carbonates on every continent that had been studied. Whatever had happened in Namibia had happened everywhere. The collapse of biological productivity was global. The glaciation was global. The cap carbonates were global. Every line of evidence pointed in the same direction. In 1998, Hoffmann, Kaufman, Halvorson, and Schrag published their findings in Science. The paper laid out the case with a precision and breadth that Kirschvink's short contribution had not attempted. Carbon isotope data, thermal subsidence analysis, cap carbonate stratigraphy, an estimated atmospheric carbon dioxide concentration at the point of escape, roughly 350 times the pre-industrial level. The paper did not merely revive the Snowball Earth hypothesis. It rebuilt it from the ground up, with evidence drawn from the physical record of a real place on a real continent. The scientific world responded. Not with unanimous agreement, that is not how science works, but with intense, focused attention. Some researchers embraced the hypothesis. Others pushed back hard. A competing model emerged almost immediately, the Slushball Earth, which proposed that the tropics had retained a band of open water or thin, seasonal ice, never fully freezing over. The Slushball camp argued that a completely ice-covered ocean was geophysically implausible, that photosynthetic life could not have survived without some access to sunlight, and that glacial sediments showing signs of cyclical melting and refreezing were inconsistent with a hard snowball. William Hyde and others modelled climate scenarios in which ice reached the deep tropics, but an equatorial strip of ocean remained open. A quasi-stable state that satisfied some of the evidence without requiring total glaciation. The debate was fierce. It remains unresolved in its details to this day. But what the 1998 paper achieved was something no previous work had managed. It made Snowball Earth impossible to ignore. It placed the hypothesis at the centre of Earth science, where it demanded a response from every geologist, geochemist, and climate modeller working on the deep past. Whether the Earth was a full snowball or a slush ball, the evidence was clear that something extraordinary had happened during the Cryogenian period. Something that froze the tropics, collapsed biological productivity, reshaped ocean chemistry, and left its signature in rocks on every continent. The question now was not whether it had happened. The question was how. What mechanism could push a planet past the point of no return, from a warm, stable world into a frozen catastrophe? The answer lay in a feedback loop so powerful that once it began, nothing on Earth could stop it. To understand what happened to the Earth during the Cryogenian, you need to understand a single, elegant, and terrifying piece of physics. It begins with a colour. Ice is white. Ocean is dark. That difference, so obvious it barely seems worth stating, is one of the most powerful forces in the entire climate system. When sunlight hits open ocean, most of it is absorbed. The water warms. The energy stays in the system. But when sunlight hits ice or snow, most of it bounces back into space. The energy is lost. The surface stays cold. This is albedo, the reflectivity of a surface, and it creates a feedback loop that can, under the right conditions, become unstoppable. Here is how it works. Imagine the Earth cooling slightly. Perhaps a small change in atmospheric composition. Perhaps a shift in ocean circulation. Perhaps a marginal decrease in the energy arriving from the sun. The cooling is modest, but it is enough to push the ice caps a little further from the poles. The ice sheets grow. As they grow, the planet's surface becomes more reflective. More sunlight is bounced away. The surface cools further. The ice grows further still. More reflection. More cooling. More ice. Each step reinforces the last. It is a positive feedback. Not positive in the sense of good, but positive in the sense of self-amplifying. The system feeds on itself. In 1969, two scientists working on opposite sides of the Cold War arrived at the same conclusion independently. At the main geophysical observatory in Leningrad, a climate physicist named Mikhail Budiko constructed one of the first mathematical models of the Earth's energy balance, a framework that accounted for incoming solar radiation, outgoing heat, and the reflectivity of the surface at different latitudes. Budiko's model was elegant in its simplicity. It reduced the climate to a set of equations that could be solved on paper, and it revealed something alarming. The ice albedo feedback had a threshold. If ice sheets advanced far enough from the poles, Budiko estimated the critical latitude at around 50 degrees. The feedback became self-sustaining. Beyond that point, no natural process could stop it. The ice would march all the way to the equator. The entire planet would freeze. At almost the same time, at the University of Arizona, an atmospheric scientist named William Sellers built his own energy balance model, using different methods but the same core physics. He reached the same conclusion. The ice albedo feedback contained a tipping point. Cross it, and the Earth locks into a frozen state with no obvious way out. Later modelling refined Budiko's threshold. The critical latitude was not 50 degrees but closer to 30, perhaps even 25 degrees from the equator. Once ice reached that far into the subtropics, the game was over. The reflectivity of the advancing ice sheets overwhelmed the warming power of the sun, and the feedback ran to completion. Total glaciation. A white planet. Every ocean sealed. Now apply this to the Neoproterozoic. the sun was 6% dimmer. That alone pushed the climate closer to the edge. The difference between a stable, ice-free Earth and a frozen one was smaller than it is today. The margin of safety was thinner. Any process that could draw enough carbon dioxide out of the atmosphere, even gradually, even over millions of years, risked tipping the balance. And the geography of the Neoproterozoic made that risk worse. Rodinia straddled the equator. The tropics, where rain is heaviest and chemical weathering is fastest, were covered in continental rock. Every rainstorm that fell on Rodinia dissolved carbon dioxide from the atmosphere and locked it into carbonate minerals on the ground. The planet was, in a sense, preloaded for catastrophe. It did not need a dramatic shock. It needed a nudge. The question that consumed geologists for years was the nature of that nudge. What, exactly, pushed the Earth past the threshold? The ice albedo feedback explained why a small cooling could become a total glaciation. But it did not explain what started the cooling in the first place. Something had to draw enough carbon dioxide out of the atmosphere to initiate the process. Something had to lower the thermostat far enough that ice could reach the critical latitude and the feedback could take over. The answer, when it came, was not a single cause. It was a conspiracy of forces, geological, chemical, and volcanic, that converged at exactly the wrong moment in the planet's history. It began with Rodinia breaking apart. Around 750 million years ago, the supercontinent that had held most of the world's landmass together for hundreds of millions of years began to fracture. Rifts opened. New coastlines formed. Fragments of continents separated and drifted, exposing fresh rock to the elements for the first time. This was not unusual in itself. Supercontinents assemble and break apart on cycles of hundreds of millions of years, and the Earth had seen it before. But the breakup of Rodinia was different in one critical respect. It happened at the equator. The rifting and volcanism associated with the breakup produced enormous volumes of fresh basalt, dark, iron-rich volcanic rock that weathers rapidly when exposed to warm, wet conditions. And the conditions at the equator were precisely warm and wet. Rainfall was heavy. Temperatures were high. The chemical reactions that break down rock and consume atmospheric carbon dioxide were running at maximum speed. In 2003, a team led by Yves Goderis at the Laboratoire des Mécanismes et Transferts en Géologie in Toulouse published a study that quantified this process. They modelled the weathering of large basaltic provinces produced by Rodinia's breakup, and showed that a basaltic area of roughly 6 million square kilometres, positioned within the equatorial belt where weathering is most efficient, could consume enough atmospheric carbon dioxide to trigger a snowball glaciation. The mechanism was slow. It operated on timescales of millions of years, but it was relentless. Every year, a little more carbon dioxide was stripped from the air and locked into the ground. Every year, the greenhouse effect weakened slightly. Every year, the Earth cooled a fraction of a degree. Goderis and his colleagues called it fire and ice, the volcanic creation of new rock driving the chemical destruction of the very greenhouse gas that kept the planet warm. But weathering alone may not have been enough. The process is gradual, and the Earth's climate system has self-correcting mechanisms that normally prevent runaway cooling. As the planet cools, weathering slows. Cold, dry conditions reduce the chemical reactions that consume carbon dioxide, allowing the gas to build back up. It is a thermostat, and it usually works. For the Earth to have crossed the threshold into a full snowball state, something may have needed to overwhelm that thermostat. something faster and more violent than slow chemical weathering. In 2010, a geologist at Harvard named Francis McDonald published a paper that changed the timeline of the entire hypothesis. Using precise uranium-lead radiometric dating from volcanic ash layers interbedded with glacial deposits in the Yukon, McDonald pinpointed the onset of the Sturtian glaciation, the first and longest of the two great cryogenian ice ages, to approximately 717 million years ago. For the first time, the start of the snowball could be dated not to within tens of millions of years, but to within a few 100,000. And that precision revealed something remarkable. The onset of the Sturtian glaciation was essentially simultaneous with the eruption of one of the largest volcanic provinces in the Neoproterozoic record, the Franklin Large Igneous Province, a vast field of basaltic lava that covered much of what is now Arctic Canada. McDonald noticed the coincidence and spent years investigating it. In 2017, working with Robin Wordsworth, an atmospheric physicist in Harvard's Department of Environmental Science and Engineering, he proposed a mechanism that could have tipped the balance. The Franklin eruptions were not ordinary basaltic flows. They were sulfur-rich, and when sulfur-rich volcanic eruptions occur at equatorial latitudes, where the sun's energy input is greatest, the sulfur dioxide injected into the stratosphere forms aerosol particles that reflect incoming sunlight with brutal efficiency. A single large eruption can cool the global climate measurably for a year or two. But the Franklin province was not a single eruption. It was a sustained volcanic episode. If the eruptions persisted for 5 years or more, and if the sulfur aerosols reached the stratosphere in sufficient quantity, the cooling effect could have been enough to push ice past the critical latitude. The weathering drawdown had already lowered carbon dioxide and cooled the planet to the brink. The volcanic aerosols provided the final shove. This is what made the Neoproterozoic snowball unique. It was not caused by one thing. It was caused by everything happening at once. A dim sun, reducing the energy available to warm the surface. A supercontinent at the equator, maximizing chemical weathering of tropical basalt. A breakup event exposing millions of square kilometres of fresh volcanic rock to the heaviest rainfall on the planet. A sustained volcanic episode injecting reflective aerosols into the atmosphere at the worst possible latitude. And an ice albedo feedback waiting in the physics of the climate system, ready to amplify any cooling past a critical point into a total irreversible glaciation. No single factor would have been sufficient. The sun had been dim for billions of years without triggering a snowball. Supercontinents had broken apart before without freezing the planet. Volcanic eruptions happen constantly and do not normally end in global catastrophe. But this particular combination, this specific alignment of geological, atmospheric, and astronomical conditions, had never occurred before in Earth's history and has never occurred since. It was, as Goderus wrote, a unique conjunction of internal forces and external conditions. Neither before nor after did this conjunction happen again. The result was precisely what Bodico's equations predicted. Ice advanced from the poles. It reached the subtropics. It crossed the threshold. And then it did not stop. Within perhaps a few million years, fast by geological standards, the ice reached the equator. The ocean sealed over. The hydrological cycle collapsed. And the planet entered a state so extreme, so alien, that nothing in the last 500 million years of Earth history comes close to resembling it. Try to picture it. You are standing on the surface of the Earth 700 million years ago, and there is nothing to see. No ocean, no land, no colour at all. From horizon to horizon, in every direction, the world is white. The ground beneath your feet is ice, not the thin, seasonal ice of a frozen lake, but a slab hundreds of metres thick, pressed down by its own colossal weight. The air is still. The temperature sits at minus 50 degrees Celsius or colder, so far below freezing that exposed skin would crystallise in minutes. There is no wind worth speaking of, because there is almost no moisture in the atmosphere to drive weather systems. There is no rain, there are no clouds or almost none. The sky above is a pale, washed out blue, and the sun, already dimmer than the one you know, hangs low and distant, its light bouncing off the ice and straight back into space. You could walk for thousands of kilometres in any direction and nothing would change. The ice stretches from pole to pole. The entire ocean is sealed beneath it. This is Snowball Earth, and it is the most alien landscape this planet has ever produced. Beneath your feet, the ice tells a story of extraordinary violence done slowly. The oceans did not freeze in a single event. They froze over millions of years, as the ice albedo feedback dragged the planet deeper into cold. At the poles, where the ice was thickest, it may have reached a kilometre or more in depth. At the equator, where residual solar energy was greatest, the ice was thinner, perhaps a few hundred metres, but still far too thick for sunlight to penetrate. The oceans beneath were cut off from the atmosphere entirely. No gas exchange, no oxygen replenishment, no connection to the sky. This created a world beneath the ice that was as hostile as the surface above it. Dissolved oxygen in the water was consumed by chemical reactions, and whatever microbial life persisted, and with no way to replace it, the oceans turned progressively anoxic. Iron, that would normally oxidize and settle out of the water column, remained dissolved, accumulating to concentrations not seen since the Archean. The deep ocean became a dark, cold, chemically alien reservoir, rich in dissolved metals, stripped of oxygen, and sealed under a lid of ice so thick it behaved like solid rock. And it did behave like rock. One of the strangest features of a fully frozen ocean is the formation of what climate scientists call sea glaciers. When ice grows thick enough, it begins to flow under its own weight, exactly as a glacier on land flows downhill under gravity. On Snowball Earth, the thickest ice formed at the poles, where temperatures were lowest and accumulation was greatest. That ice flowed slowly toward the equator, driven by the pressure gradient between thick polar ice and thinner tropical ice. Modelling by Jason Goodman and Raymond Pierre Humbert showed that these sea glaciers would have crept across the ocean surface at rates of centimetres to metres per year, imperceptible on human timescales, but over millions of years, enough to create a dynamic, flowing ice shell that redistributed frozen mass from high latitudes to low. The equator became the ablation zone, the region where ice was thinnest, where the faint tropical sun provided just enough energy to sublimate the surface without melting it. Ice did not melt at the equator. It sublimated, passed directly from solid to vapour without ever becoming liquid water. The vapour rose into the thin, dry atmosphere and was carried poleward, where it condensed and fell as snow, feeding the polar ice sheets and completing the cycle. It was a hydrological cycle of sorts, but a ghost of the one you know. No rivers, no rain, no liquid water touching the surface anywhere on the planet. The silence would have been absolute. No waves, no wind-driven spray, no cracking of seasonal ice. The only sounds on the surface of Snowball Earth would have been the occasional groan of ice shifting under pressure, the distant rumble of a volcano forcing its way through the frozen crust, and nothing else. For tens of millions of years. And yet the planet was not dead. Beneath the ice, beneath the frozen ocean, the Earth's interior continued to churn. Mantle convection did not stop. Tectonic plates continued to move. Mid-ocean ridges continued to spread, and volcanoes continued to erupt, punching through ice sheets on land, venting gases through fractures in the seafloor, releasing carbon dioxide and sulfur dioxide and water vapour into an atmosphere that had no way to scrub them clean. The volcanoes did not care about the ice. They operated on a time scale and an energy source entirely independent of what was happening at the surface. And every eruption added a little more carbon dioxide to the atmosphere. Every year, a little more. Every century, a little more. The gas accumulated because the mechanism that normally removes it, chemical weathering by rainfall, had been shut down completely. The thermostat was broken, and the greenhouse gas was building toward levels the planet had not experienced in billions of years. That build-up would eventually end the snowball, but not yet. Not for millions of years. For now, the planet sat frozen, sealed and waiting. A white marble suspended in space, reflecting most of the sunlight that reached it, locked in a state that seemed permanent and inescapable. The most patient trap in the history of the Earth. Here is what makes Snowball Earth more than an hypothesis. It left evidence. Not subtle, ambiguous evidence that requires sophisticated instruments and statistical arguments to interpret, but physical, tangible, unmistakable evidence carved into rock, pressed into sediment, and preserved across hundreds of millions of years on every continent that has been studied. The frozen planet wrote its own testimony, and that testimony is still readable today. The most direct evidence comes from tillites, rocks formed from glacial debris. When a glacier moves across a landscape, it picks up everything in its path. Boulders, gravel, sand, clay. It grinds them together, mixes them without sorting, and deposits them as a chaotic, unsorted mass called diamictite. Tillites are the lithified version of this material. Ancient diamictites that have been compressed and cemented into solid rock over geological time. They are distinctive. No other geological process produces the same signature. The jumble of grain sizes, the angular fragments, the total absence of the sorting that rivers or wind would produce. When you find a tillite, you have found a glacier. Neoproterozoic tillites have been identified on every major continent. They appear in Australia, in Namibia, in Canada, in China, in Scotland, in Brazil, in Svalbard, in India. And the critical point, the point that turns a regional glaciation into a planetary one, is where those continents were when the tillites formed. Paleomagnetic analysis of the rocks bracketing these deposits consistently places them at low latitudes, not near the poles, where glaciers are expected. Near the equator, where glaciers should be impossible. Paleomagnetism works because certain minerals in sedimentary and volcanic rocks, particularly magnetite and hematite, align with the Earth's magnetic field at the time the rock forms. By measuring the direction and inclination of this remnant magnetization, geologists can calculate the latitude at which a rock was deposited, regardless of where the continent has since drifted. The technique is not without its complications. Rocks can be remagnetized by later heating events, and as some formations preserve their original magnetic signature more reliably than others. But when multiple independent studies, using different rock types from different continents, consistently return tropical paleolatitudes for Neoproterozoic glacial deposits, the signal becomes very difficult to dismiss. alongside the tillites, there are striated surfaces, smooth bedrock faces scored with parallel scratches where ice ground across them under enormous pressure. These striations are the fingerprints of moving ice, as distinctive as a glacier's calling card. They have been found in Neoproterozoic rocks at paleolatitudes that place them squarely within the tropics. And there are dropstones, isolated rocks, sometimes the size of a fist, sometimes larger, found embedded in finely laminated marine sediments. They are too large and too angular to have been carried by currents. They fell from above, released from the base of a floating iceberg or ice shelf as it drifted over open or partially open water, dropping its cargo into the quiet sediment below. Drop stones in Neoproterozoic marine deposits tell you that ice was present over the ocean, calving and drifting in regions where the latitude says ice had no business being. But the most striking piece of physical evidence arrived in 2024 from an unexpected place. A team led by Lorraine Courtney Davies at the University of Colorado Boulder published a study in the Proceedings of the National Academy of Sciences that examined the Tava sandstone, a formation found in the Front Range of Colorado, injected as vertical dikes and sills into the billion-year-old Pikes Peak granite. The Tava sandstone is not a surface deposit. It was forced downward, pushed into cracks and fractures in the underlying bedrock by immense pressure from above. The team demonstrated that this pressure came from a continental ice sheet, a glacier sitting on top of equatorial Colorado, pressing sand into the fractured granite beneath it with a force that could only be produced by ice hundreds of meters thick. Think about what that means. Colorado, 700 million years ago, sat near the equator. Not at a high latitude, not on the edge of a polar ice cap, but in the heart of the tropics. And there was an ice sheet on top of it, so massive that it injected sand into solid granite. This is not coastal glaciation. This is not a tongue of ice reaching down from higher latitudes. This is ice forming in the hottest part of the planet, on the interior of a continent, far from any ocean influence. The Tava sandstone is evidence of glaciation at the very centre of equatorial land, precisely the kind of deposit that a Snowball Earth would produce and that virtually nothing else could explain. The physical evidence, tillites, striations, dropstones, and now the extraordinary Tava sandstone, tells a consistent story. Ice was everywhere. It reached the tropics. It covered continents that sat on the equator. It extended across oceans in every hemisphere. No regional glaciation, no matter how severe, can account for glacial deposits at every latitude on every continent simultaneously. The evidence demands something global, something total, something that, until a geophysicist at Caltech gave it a name, seemed too extreme to be real. But rocks do not exaggerate, they do not speculate. They record what happened, and they keep that record for as long as the planet holds together. And what the rocks of the Cryogenian record is a planet that froze from pole to pole, not once, but at least twice, and left its signature in stone so clearly that 700 million years of tectonic rearrangement, erosion, burial, and metamorphism could not erase it. The evidence survived because the event was that large. And the event was that large because the physics that drove it, once triggered, had no off switch. What comes next is the chemistry. The rocks tell you where the ice was. The isotopes tell you what the ice did to the living world beneath it. The rocks tell you that ice was there. They show you where it sat, how it moved, and how far it reached. But rocks are blunt instruments. They record physical presence, the weight of a glacier, the scrape of a moving ice sheet, the drop of a stone from a drifting berg. What they cannot tell you, on their own, is what happened to the world beneath the ice. For that, you need chemistry. And the chemistry of Snowball Earth is written in atoms. Every living organism on this planet has a preference. When photosynthetic life, cyanobacteria, algae, plants, pulls carbon from its environment to build organic molecules, it does not treat all carbon atoms equally. Carbon exists in two stable forms: carbon-12, which is lighter, and carbon-13, which is heavier. Photosynthetic organisms preferentially absorb carbon-12. They find it slightly easier to incorporate into their biochemistry, and over billions of years and trillions of organisms, that tiny preference creates a measurable signature in the chemistry of the ocean. When photosynthesis is active and productive, the surface water becomes enriched in carbon-13, because the lighter carbon-12 is being pulled out by biology and locked into organic matter. The ratio of carbon-13 to carbon-12 in seawater, and in the carbonate minerals that precipitate from that water, becomes a direct proxy for biological productivity. When life is thriving, the ratio shifts one way. When life collapses, it shifts the other. This is isotope fractionation, and it is one of the most powerful tools in the geochemist's arsenal. Carbonate rocks formed in ancient oceans preserve the isotopic composition of the water they precipitated from, like a chemical snapshot frozen in stone. Measure the carbon isotopes in a sequence of carbonate rocks laid down over millions of years, and you can reconstruct the rise and fall of biological productivity in those ancient seas with remarkable precision. In 1997, a team led by Alan Kaufman, working with Andrew Knoll at Harvard and Guy Narbonne at Queen's University, published a framework for using carbon isotope stratigraphy to correlate Neoproterozoic glacial events across different continents. The principle was straightforward, but the implications were enormous. If the same isotopic excursion, the same sudden crash in the carbon-13 to carbon-12 ratio, appeared in carbonate rocks of the same age on multiple continents, it meant that whatever caused the crash was global, not a regional disruption, not a local change in ocean circulation. A planetary collapse of photosynthetic productivity recorded simultaneously in rocks on opposite sides of the world. That is exactly what they found. The carbon isotope record before each cryogenian glaciation shows normal values, the signature of a functioning biosphere, with photosynthetic organisms pulling carbon-12 from the surface ocean at the usual rate. Then, at the onset of glaciation, the ratio plunges. It drops sharply and stays low for the duration of the glacial period, millions of years of depressed values, indicating that biological productivity in the surface ocean had effectively ceased. The surface was dark, the ice had sealed it off from sunlight. The photosynthetic engine that had driven ocean chemistry for billions of years had been shut down. In 2005, Galen Halvorson and colleagues assembled the most comprehensive composite carbon isotope record for the Neoproterozoic yet produced, stitching together data from carbonate sections across multiple continents into a single continuous curve spanning hundreds of millions of years. The curve is striking. It shows two massive negative excursions, each coinciding precisely with the two known cryogenian glaciations. The excursions are not subtle dips. They are some of the largest perturbations in the entire carbon isotope record of Earth history. Drops so extreme that they can only be explained by a near total shutdown of photosynthesis in the global ocean over geological timescales. But the carbon isotopes are not alone. Banded iron formations, those distinctive layered deposits of iron oxide and silica that had vanished from the geological record over 1 billion years earlier, reappear in Neoproterozoic sediments deposited during the glaciations. Their return demands anoxic oceans. Iron dissolves in water that lacks oxygen and accumulates over time. When that water is finally exposed to oxygen, when the ice breaks and the atmosphere touches the sea surface again, the iron oxidizes instantly and rains down onto the seafloor as rust. The billion-year absence of banded iron formations, followed by their sudden return during the Cryogenian, is one of the most dramatic signals in the entire geological record. It means the oceans lost their oxygen. It means they were sealed. It means the conditions that had not existed on Earth since the early Proterozoic had returned. Then there is strontium. The ratio of strontium-87 to strontium-86 in seawater is controlled by two competing sources: the weathering of continental rocks, which delivers radiogenic strontium-87, and the interaction of seawater with fresh volcanic basalt at mid-ocean ridges, which delivers less radiogenic strontium-86. When continental weathering is intense, the ratio rises. When it slows or stops, the ratio falls. The strontium isotope record across the Cryogenian glaciations shows precisely the pattern you would expect from a frozen planet. A decline in continental weathering signatures during the glaciation, followed by a sharp spike immediately after deglaciation, when the most intense chemical weathering event in Earth history flushed radiogenic strontium from freshly exposed rock into the post-glacial ocean. And in 2014, a team led by Alan Rooney at Harvard and Yale added yet another isotopic line of evidence. Working with rhenium and osmium isotopes extracted from organic-rich shales in the Rapitan group of northwestern Canada, Rooney and colleagues demonstrated that the onset and duration of the Sturtian glaciation could be dated independently of the uranium-led methods used on volcanic ash layers. The osmium isotope data confirmed what the other systems were showing. The Sturtian glaciation began around 717 million years ago and lasted approximately 57 million years. Multiple isotopic systems, measuring different elements, governed by different chemical processes, all converging on the same answer. This is what makes the geochemical case for Snowball Earth so difficult to dismiss. It is not built on a single line of evidence. Carbon isotopes tell you that photosynthesis collapsed. Banded iron formations tell you that the oceans went anoxic. Strontium isotopes tell you that continental weathering shut down and then exploded back to life. Osmium isotopes confirm the timing independently. Each system operates on different chemistry, responds to different environmental variables, and is measured using different laboratory techniques. And all of them point to the same event: a global glaciation so complete that it restructured the chemistry of the entire ocean for tens of millions of years. The chemical fingerprints do not merely support the Snowball Earth hypothesis, they demand it. No other known mechanism can simultaneously explain the collapse of biological productivity, the return of banded iron formations after a billion-year absence, the shutdown of continental weathering, and the explosive chemical rebound that followed the glaciation. The isotopes are not ambiguous. They are not open to multiple interpretations. They record a planet that was sealed, darkened, and chemically transformed. And they record it on every continent that preserves rocks of this age. But there is something else the chemistry reveals. Something that makes the story of Snowball Earth even stranger than a single catastrophic freeze. It happened more than once. The Earth did not freeze and thaw in a single episode. It froze, thawed, recovered, and then froze again. The Cryogenian period, named precisely because of these events, contains two distinct, well-documented global glaciations separated by a gap of millions of years during which conditions returned to something approaching normal. 2 separate descents into planetary ice cover. 2 separate escapes. 2 separate chemical catastrophes recorded in the rock record with unmistakable clarity. The first was the Sturtian glaciation. It began approximately 717 million years ago. The date pinpointed by Francis MacDonald's uranium lead work on volcanic ash layers in the Yukon. And it did not end for roughly 57 million years. 57 million years. That number deserves a moment to settle. The entire age of the dinosaurs, from the first theropods to the asteroid that ended them, fits inside roughly 170 million years. The Sturtian glaciation lasted a third of that span. Ice covered the planet for longer than the entire Cenozoic era. The age of mammals, the rise of primates, the evolution of humans, the entirety of recorded civilization. All of that fits inside the time the Sturtian ice sat on the Earth and did not move. The second was the Marinoan glaciation. It began approximately 650 million years ago. After an interglacial period of perhaps 10 to 25 million years, during which the planet recovered, the oceans reopened, and biological productivity resumed. Then the ice returned. The Marinoan was shorter, roughly 15 million years from onset to termination, but the evidence suggests it was equally extreme. Tillites at tropical paleolatitudes, carbon isotope excursions of comparable magnitude, cap carbonates of equivalent thickness and global distribution. The deglaciation was pinpointed with exceptional precision by Daniel Condon and colleagues in 2005, who used uranium-lead dating of zircon crystals from volcanic ash beds in Namibia to place the Marinoan termination at approximately 635 million years ago. It remains one of the most precisely dated events in the entire Precambrian record. The fact that the Sturtian lasted nearly 4 times longer than the Marinoan raises questions that remain actively debated. The escape mechanism, volcanic carbon dioxide accumulating until the greenhouse effect overwhelmed the ice albedo, should have operated on a similar timescale in both cases. One possibility is that the continental configuration was different during the Marinoan, with less tropical land available for weathering, meaning that carbon dioxide was not drawn down as aggressively, and the threshold for glaciation was crossed at a different atmospheric concentration. Another is that the volcanic carbon dioxide flux was higher during the Marinoan, shortening the accumulation time. A third possibility is that the ice was not as complete during the Marinoan, that thin ice or open water persisted in patches, allowing some weathering to continue, and some carbon dioxide to be removed even during the glaciation, slowing the build-up but not preventing the eventual escape. The data do not yet settle the question. What the data do show is that the cryogenian was not unique in Earth history, merely the most extreme example of a phenomenon the planet has experienced before. Around 2.4 billion years ago, during the Paleoproterozoic, the Earth appears to have undergone a similar episode. The Huronian glaciation, named after rocks near Lake Huron in Ontario, produced glacial deposits at tropical paleolatitudes and coincided with the Great Oxidation Event, when rising atmospheric oxygen may have destroyed the methane greenhouse that had kept the early Earth warm. Kirschvink and colleagues argued in 2000 that this earlier event also represented a snowball state, though the evidence is less complete and the details remain more uncertain than are for the cryogenian. Later still, around 580 million years ago, the Gaskia's glaciation left glacial deposits in Newfoundland and a handful of other locations. It was shorter, perhaps 1 million years or less, and the evidence for global ice cover is weaker. Most researchers consider Gaskia a severe but regional glaciation, not a full snowball. It sits at the boundary between the Ediacaran period and the emergence of complex life, and its relationship to the earlier cryogenian events, if any, remains unclear. But it is the cryogenian that stands alone. No other period in Earth history produced 2 back-to-back global glaciations of this magnitude and duration. No other period left such an unambiguous chemical and physical record on every continent. And no other period was followed by such a dramatic transformation of the living world. The Sturtian and Marinoan glaciations were not merely climate events. They were planetary scale experiments, tests of how much the Earth could endure and still recover. The planet passed both tests. Life survived. The climate system righted itself. And what emerged from the ice was a world fundamentally different from the one that had entered it. A world primed for an explosion of biological complexity unlike anything in the preceding 3 billion years of Earth history. The question of how life survived is, in many ways, the most extraordinary part of the entire story. Tens of millions of years of darkness, cold, and chemical hostility, and yet, when the ice broke, the biosphere was not merely intact, it was ready. Here is the part of the story that should not work. Everything you have heard so far, the ice advancing to the equator, the oceans sealed beneath hundreds of meters of frozen cover, the atmosphere cut off from the sea, the collapse of photosynthesis across the entire surface ocean, points to a world that should have been, by any reasonable biological standard, uninhabitable. Not difficult, not harsh. Uninhabitable. The Sturtian glaciation alone lasted 57 million years. The Marinoan added another 15. For a combined total of over 70 million years, the surface of this planet was locked under ice so thick that the sunlight could not reach the water beneath it. The energy source that powers nearly every ecosystem on Earth, photosynthesis, the conversion of light into life, was effectively switched off. Not reduced, not diminished, switched off. And yet life survived. This is not a minor detail. This is the central paradox of the entire Snowball Earth story. When the ice finally broke, when the greenhouse warming of accumulated volcanic carbon dioxide overwhelmed the albedo of a frozen planet, and the oceans saw sunlight again for the first time in millions of years, life was there. Not just bacterial life clinging to existence in a few isolated pockets. Diverse life, cyanobacteria, eukaryotic algae, protists, possibly even the earliest lineages of animals. The molecular clock evidence, genetic analyses that estimate when lineages diverged based on the rate of mutation, suggests that many of the major branches of eukaryotic life, and potentially the earliest metazoan lineages, were already established before or during the cryogenian glaciations. Work by Douglas Irwin and colleagues, published in 2011, placed the divergence of key animal phyla deep enough in time that some of these lineages would have had to survive through at least one snowball event. If those estimates are correct, the ancestors of every animal alive today, including you, endured the longest, coldest, darkest catastrophe this planet has ever produced. And they did not merely endure it, they emerged from it ready to diversify. The fossil record immediately following the Marinoan glaciation does not show a depleted, bottlenecked biosphere struggling to rebuild from near extinction. It shows a biosphere poised for expansion. There is no clear signal of a catastrophic mass extinction in the genetic or fossil data. No severe pruning of lineages, no dramatic reduction in diversity that would indicate life was nearly wiped out. something kept it going. Something sustained enough biological diversity through tens of millions of years of ice to seed the most extraordinary evolutionary radiation in the history of the planet. The question is where? Where, on a frozen Earth, could life have hidden? This is not a question with a single answer. It is a question with several partial answers, each covering a different kind of organism and a different kind of refuge. The survival of life through Snowball Earth almost certainly depended on multiple refugia operating simultaneously. Different environments sustained by different energy sources, sheltering different communities. No single hiding place could have done the job alone. Together they may have been enough. The most secure refuge was the one that needed no sunlight at all. Deep on the ocean floor, along the mid-ocean ridges, and at scattered volcanic vents, the Earth's interior provided a source of energy entirely independent of the surface. Hydrothermal vents release superheated water rich in dissolved chemicals, hydrogen sulfide, methane, dissolved metals, that chemosynthetic microorganisms can exploit as an energy source. These are not photosynthetic organisms. They do not need light. They build their organic molecules using chemical energy drawn from the interaction between hot volcanic fluids and cold seawater. Hydrothermal vent communities exist today in the deepest, darkest parts of the ocean, thriving in conditions that would kill most surface life instantly. During a snowball, these systems would have continued operating without interruption. The ice above was irrelevant to them. The sealed ocean was irrelevant to them. As long as the Earth's interior remained active, and it did, the vents would have sustained microbial communities through any duration of glaciation. They are the ultimate biological insurance policy, life powered by the planet itself. But hydrothermal vents could only shelter chemosynthetic organisms. They could not have preserved the photosynthetic lineages, the cyanobacteria and eukaryotic algae, that clearly survived the snowball and went on to dominate the post-glacial ocean. For photosynthesizers, survival required light, and on a frozen planet, light was the scarcest resource of all. This is where the ice itself becomes important. In 2016, Paul Hoffman published a detailed model of what happens when dust and volcanic ash accumulate on the surface of a tropical sea glacier. The equatorial zone of a Snowball Earth would have been the ablation zone, the region where ice was thinnest and where sublimation slowly removed material from the surface. But it was also the region where wind-blown dust, volcanic ash from continuing eruptions, and fine debris from exposed rock surfaces would have settled onto the ice. Dark particles on white ice absorb solar radiation. They warm their immediate surroundings. And if enough dark material accumulates in one place, it can melt the ice beneath it, creating small pools of liquid water sitting on or within the glacier surface. These are cryoconite pans, shallow, transient meltwater pools sustained by the thermal contrast between dark sediment and bright ice. Cryoconite pans exist today on glaciers across the world, and they are far from lifeless. They host thriving microbial communities, cyanobacteria, green algae, tardigrades, rotifers, and other microscopic organisms, sustained by the thin sliver of sunlight that reaches through the ice or directly into the open pool. On modern glaciers, these pans are small, ephemeral, and isolated. But on Snowball Earth, the equatorial ablation zone would have stretched for thousands of kilometres, and the accumulation of volcanic ash from millions of years of continuing eruptions would have been substantial. Hoffman's model proposed that cryoconite pans in this zone could have been large enough, numerous enough, and persistent enough to sustain photosynthetic microbial communities through the entire glaciation. Not comfortably, not abundantly, but enough. The idea gained powerful support from modern analogue studies. On the McMurdo ice shelf in Antarctica, researchers have documented meltwater ecosystems that exist in conditions startlingly similar to those proposed for Snowball Earth. In 2025, a study led by Shah Hussain and colleagues, published in Nature Communications, examined the eukaryotic diversity of meltwater ponds on the McMurdo ice shelf. Shallow pools formed where dark sediment on the ice surface absorbs enough solar energy to create liquid water habitats in one of the coldest environments on the modern planet. The results were remarkable. These ponds did not host a handful of hardy survivors. They contained diverse eukaryotic communities, algae, ciliates, flagellates, demonstrating that complex microbial ecosystems can persist in ice-dominated environments with minimal energy input. The McMurdo ponds are not a perfect analogue for Snowball Earth. They are warmer, they receive more sunlight, and they exist in a world with a functioning atmosphere and nearby open ocean. But they demonstrate a principle, that photosynthetic life can maintain diverse communities on and within ice, sustained by nothing more than dark sediment and weak sunlight. Earlier work by Warwick Vincent and colleagues, published in 2000, had already shown that cyanobacterial mats in Antarctic ice-covered lakes could sustain photosynthesis under ice several meters thick, using the small fraction of light that penetrated to the water below. Ian Hawes and his team extended this in 2018 with detailed studies of microbial communities in the dirty ice of the McMurdo Shelf, demonstrating that even in the most marginal conditions, where light levels are barely above the minimum threshold for photosynthesis, life finds a way to persist. These modern ecosystems are the closest living analogues to the refugia that may have kept photosynthetic life alive through the cryogenian. But cryoconite pans and ice surface pools may not have been the only photosynthetic refugia. If the slushball model is even partially correct, if thin ice or open water persisted in patches near the equator, then pockets of habitable ocean may have remained accessible to sunlight throughout the glaciation. Even a snowball that was 99% frozen would have left room for life if that remaining 1% sat in the right place. The tropics, where solar energy input was greatest and ice was thinnest, would have been the most likely location for such patches. Whether these patches existed is one of the key unresolved questions of the entire hypothesis, and it is a question with direct biological consequences, because the diversity of life that emerged from the snowball suggests that more than just deep ocean chemosynthesizers and surface ice cyanobacteria survived. There is one more category of refuge worth considering, and it lies beneath the ice sheets themselves. Where glaciers sit on continental rock, the pressure of the overlying ice and the geothermal heat from below can create a thin layer of liquid water at the base of the glacier. These subglacial environments are dark, cold and isolated, but they are liquid, and they contain dissolved nutrients leached from the bedrock. Modern subglacial lakes beneath the Antarctic ice sheet, Lake Vostok being the most famous, have been shown to harbour microbial life sustained by chemical energy from rock-water interactions. On Snowball Earth, similar environments would have existed beneath every continental ice sheet, creating a network of isolated but habitable pockets scattered across the frozen land masses. These subglacial refugia could not have sustained photosynthetic life, but they could have preserved chemolithotrophic microorganisms, bacteria that derive energy from the chemical reactions between water and mineral surfaces, through the entire glaciation. And then there is the plumbing. The ice was not a monolith. It was a dynamic system, with cracks, fractures, meltwater channels, and conduits connecting surface environments to the ocean below. In glacial meltwater networks, channels and pockets of liquid water within the body of the ice itself could have served as pathways linking cryoconite pans on the surface to subglacial environments and ultimately to the sealed ocean beneath. These networks would have been intermittent and unstable, but over millions of years they could have facilitated the exchange of organisms, nutrients, and organic matter between different refugia, preventing complete isolation and allowing genetic material to flow between communities that would otherwise have been cut off from each other entirely. The picture that emerges is not one of life barely clinging to existence in a single precarious refuge. It is one of life distributed across multiple environments: deep ocean vents, surface ice pools, subglacial lakes, thin ice patches, inglacial channels, each sustaining different communities, each connected to the others through geological and hydrological processes operating on timescales of thousands to millions of years. The Snowball did not offer life a single lifeboat. It offered a fleet of them, scattered across a frozen ocean, each too small and too fragile to guarantee survival on its own, but collectively sufficient to carry the biosphere through the longest winter in Earth's history. That the biosphere survived at all is extraordinary. That it survived with enough diversity to fuel the most dramatic evolutionary radiation the planet has ever seen is something close to miraculous, though the mechanisms behind it are entirely physical, entirely chemical, and entirely consistent with the laws that govern this planet. Life did not need a miracle to survive Snowball Earth. It needed rock, heat, dust, and light, and it found just enough of each to hold on. What it could not do, from its scattered refugia, was end the glaciation. That required a different force entirely, one that had been building, invisibly and relentlessly, in the atmosphere above the ice for every single year of the frozen world's existence. While the surface of the Earth sat frozen and the oceans lay sealed beneath their lid of ice, something was happening in the atmosphere that no force on the planet could prevent. Volcanoes were erupting. They had never stopped. The ice could silence the wind, shut down the rain, freeze the rivers, and seal the ocean from the sky, but it could not reach into the mantle. It could not stop the convective engine that drives the Earth's interior. Tectonic plates continued to spread. Magma continued to rise, and every eruption, whether it broke through a continental ice sheet, vented through a fracture in the seafloor, or punched through a volcanic island arc, released gases into the atmosphere. Water vapour, sulfur dioxide, and carbon dioxide. Under normal conditions, carbon dioxide does not accumulate in the atmosphere for long. It is removed by a process so fundamental to the Earth's climate that it functions as a planetary thermostat. Rain falls. Rainwater absorbs carbon dioxide from the air, forming a weak carbonic acid. That acid reacts with exposed rock, particularly silicate minerals, dissolving them and releasing calcium, magnesium, and bicarbonate ions into solution. Rivers carry these dissolved products to the ocean, where they combine and precipitate as carbonate minerals on the seafloor. The carbon dioxide that started in the atmosphere ends up locked in stone. This is the silicate weathering cycle, and it has regulated the Earth's temperature for billions of years. When the planet warms, weathering speeds up, pulling more carbon dioxide from the air and cooling the surface. When the planet cools, weathering slows, allowing carbon dioxide to accumulate and warming the surface again. It is self-correcting, elegant, and, under every condition the Earth had experienced for the previous 3 billion years, sufficient. The snowball broke it. On a frozen planet, there is no rain. There are no rivers. Exposed rock is buried under ice or locked in permafrost. The chemical reactions that consume atmospheric carbon dioxide cannot proceed. The sink vanishes, but the source does not. Volcanoes continue to emit carbon dioxide at roughly the same rate they always have, an estimated 50 to 100 million tonnes per year from all sources combined. In a normal climate, this is balanced by weathering. On a frozen Earth, it is balanced by nothing. The gas accumulates, year after year, century after century, for millions of years. In 1992, Ken Caldeira and James Casting published a foundational analysis of this process. Working at Penn State and building on earlier atmospheric modelling, they calculated how long it would take volcanic carbon dioxide to accumulate to levels sufficient to overcome the ice albedo feedback and trigger deglaciation. Their estimates placed the threshold at roughly 0.12 bars of carbon dioxide partial pressure, approximately 350 times the pre-industrial atmospheric concentration. Later modelling by Guillaume Le Hire and colleagues in 2008 refined these estimates, exploring how the timescale varied depending on volcanic outgassing rates, ice thickness, and whether volcanic ash darkening the ice surface could accelerate the process by reducing the planet's overall albedo. Le Hire's models suggested that the carbon dioxide buildup alone, without any additional forcing, would take between 5 and 30 million years to reach the deglaciation threshold, a range consistent with the observed durations of the Sturtian and Marinoan glaciations. Think about what this means in practical terms. For the entire duration of the Sturtian glaciation, 57 million years, carbon dioxide was accumulating in the atmosphere with nowhere to go. At a conservative volcanic emission rate, the total quantity of carbon dioxide added to the atmosphere over that period was staggering. By the time the threshold was reached, the atmosphere held more carbon dioxide than at any point since the Archean. The planet was wrapped in a greenhouse blanket so thick that even a surface reflecting most of the sun's energy back into space could no longer hold back the warming. And here is the irony that sits at the heart of this entire story. Carbon dioxide was the victim and the saviour. The drawdown of atmospheric carbon dioxide, by tropical weathering of basalt, by the chemical consumption of the gas on Rodinia's equatorial continents, was what triggered the snowball in the first place. The ice albedo feedback amplified the cooling, but the initial push came from carbon dioxide being pulled from the atmosphere faster than volcanoes could replace it. The planet froze because it lost its greenhouse gas, and the planet thawed because, once frozen, it could not stop that same gas from building back up. The thermostat that normally prevents both extremes, the weathering cycle that adds carbon dioxide when it is cold and removes it when it is warm, was the mechanism that failed going in and the mechanism that rescued the planet coming out. Carbon dioxide created the trap. Carbon dioxide sprung the trap. The molecule that nearly killed the biosphere was the molecule that saved it. By the time the atmosphere reached the critical concentration, the planet had been frozen for longer than most geological periods last. The ice was ancient. The oceans beneath were anoxic, iron-rich, and utterly transformed. And above it all, an atmosphere loaded with more greenhouse gas than the modern world can easily comprehend was pressing down on a surface that could no longer hold it at bay. What happened next was the most violent climate reversal in the history of the Earth. The thaw did not begin gradually. It began at the equator, the one place where the ice was thinnest, where the faint tropical sun delivered the most energy per square metre, and where the accumulated greenhouse warming first overwhelmed the reflective power of the surface. the ice at the equator had always been the weakest link in the Snowball's armour. Sea glaciers flowing from the poles thinned as they approached the tropics. Sublimation removed material from the surface. Volcanic ash darkened patches of ice, increasing local absorption of sunlight. And the relentless build-up of carbon dioxide had been warming the atmosphere for millions of years, incrementally, invisibly, until the energy balance at the equator tipped. When the first cracks appeared, when the first patches of dark ocean were exposed to direct sunlight for the first time in millions of years, the same feedback that had frozen the planet now ran in reverse. Dark water absorbs sunlight. It warms. It melts the ice around it. More dark water is exposed. More sunlight is absorbed. Did the ice albedo feedback, which had been the engine of the freeze, became the engine of the thaw? And this time the feedback was not fighting against a cooling atmosphere. It was accelerating into a greenhouse so extreme that the warming had nowhere to go but up. The deglaciation was catastrophically fast. Climate models suggest that once the equatorial ice broke, the entire planet could have transitioned from fully frozen to ice-free in as little as a few thousand years, perhaps less. By geological standards, this is instantaneous. The Sturtian glaciation lasted 57 million years. The thaw that ended it may have taken less than 10,000. The asymmetry is breathtaking. Millions of years to freeze, thousands of years to melt. The planet swung from one extreme to the other in a geological blink. And the world that emerged from the ice was not the world that had entered it. Surface temperatures soared. The atmosphere, now carrying hundreds of times the modern concentration of carbon dioxide, trapped heat with ferocious efficiency. Global mean temperatures may have reached 50 degrees Celsius or higher in the immediate aftermath. A hothouse so extreme that the tropical oceans would have been too warm for most modern marine life. Rain returned, and it returned with violence. The atmosphere, suddenly saturated with moisture evaporating from newly exposed oceans, produced rainfall of extraordinary intensity. This rain absorbed carbon dioxide from the overloaded atmosphere, forming carbonic acid, and attacked every exposed rock surface with a chemical ferocity that dwarfed anything in the modern weathering cycle. Rivers reformed, deltas expanded, and the dissolved products of this apocalyptic weathering, calcium, magnesium, bicarbonate, phosphorus, iron, flooded into the oceans in quantities that had no precedent in the preceding billion years. This is where the cap carbonates come from. The warm, carbon dioxide saturated ocean suddenly receiving an enormous influx of dissolved calcium and bicarbonate from continental weathering, became supersaturated with calcium carbonate almost immediately. Carbonate minerals precipitated directly from the water column, not built by organisms, not deposited gradually over millions of years, but chemically dumped onto the seafloor in a geologically instantaneous event. The result is a distinctive layer of carbonate rock, usually dolostone or limestone, sitting directly on top of the glacial deposits, with a contact so sharp it looks like someone drew a line between two different worlds. Below the line, glacial debris, the rubble of a frozen planet. Above the line, warm water carbonate, the chemical signature of an extreme greenhouse. The transition between them represents one of the most dramatic environmental swings in the history of the Earth, compressed into a few thousand years of sedimentary record. The cap carbonates are extraordinary not just for their chemistry, but for their physical structures. Within them, geologists have found giant wave ripples, symmetrical ripple marks with wavelengths of meters, formed by powerful storm waves rolling across shallow seas with no coastline to stop them. crystal fans of aragonite, delicate branching mineral growths that precipitated directly from seawater, so saturated with carbonate that crystals grew on the seafloor like underwater frost. Barite inclusions. Crystals of barium sulfate that formed when barium-rich deep water, released from the anoxic ocean beneath the melting ice, mixed with sulfate-bearing surface water for the first time. Each structure tells a piece of the deglaciation story. Violent storms, extreme chemical saturation, and the sudden mixing of ocean layers that had been separated for millions of years. In 2016, Thomas Gernon and colleagues proposed an additional mechanism for the extraordinary volume of cap carbonates. They suggested that the rapid exposure of mid-ocean ridges during deglaciation, as ice retreated and sea level shifted, led to the eruption and rapid alteration of volcanic glass along shallow ridge systems. This glass, when it reacts with seawater, releases enormous quantities of alkalinity, dissolved ions that drive carbonate precipitation. Gernon's shallow ridge hypothesis added a new source of chemical input to the post-glacial ocean, supplementing continental weathering and helping to explain how cap carbonates could form so quickly and so uniformly across the entire planet. The cap carbonates are found on every continent that preserves Neoproterozoic sediments. They are found at every paleolatitude. They are found above both Sturtian and Marinoan glacial deposits. Their global distribution, their chemical uniformity, and their position directly above glacial layers make them one of the most recognisable and diagnostic features of the Snowball Earth record. They are, in a very real sense, the receipt, the chemical proof that the planet swung from total glaciation to extreme greenhouse in the span of a geological instant, and that the mechanism of escape was precisely what Kirschvink proposed in 1992, volcanic carbon dioxide, building without limit in a sealed atmosphere until the greenhouse effect overwhelmed the ice. The thaw was not a recovery, it was a second catastrophe, a transition from one extreme to another, from a planet too cold for liquid water to a planet almost too hot for life as we know it. The biosphere that had survived the ice now had to survive the heat, but it did more than survive. The chemical violence of the deglaciation, the weathering, the nutrient flush, the oxygenation that followed, created conditions that had never existed before on Earth. Conditions that would reshape the trajectory of life on this planet forever. The world that emerged from beneath the Marinoan ice 635 million years ago was unrecognisable. The glaciation had lasted roughly 15 million years. The thaw had taken perhaps a few thousand. And the planet that now baked under an atmosphere saturated with carbon dioxide bore no resemblance to the frozen sphere it had been just a geological heartbeat earlier. Surface temperatures climbed to levels not seen in billions of years. Rainfall of extraordinary intensity scoured every exposed landmass, dissolving rock with carbonic acid and flushing the dissolved remains into swollen rivers that carried them to the sea. The oceans, freshly opened and warming rapidly, received this chemical deluge like a patient receiving a massive transfusion, and the effect on ocean chemistry was immediate and transformative. Phosphorus was the key. Of all the nutrients carried from weathered continental rock into the post-glacial ocean, phosphorus mattered most. It is the limiting nutrient for biological productivity in most marine environments, the element that, when scarce, holds the entire food web in check. Under normal conditions, phosphorus enters the ocean slowly, delivered by steady weathering of continental rock over millions of years. But the post-snowball weathering event was not normal. It was the most intense chemical weathering episode in at least 1 billion years, driven by an atmosphere carrying hundreds of times the modern concentration of carbon dioxide and rainfall rates that dwarfed anything in the recent geological record. The quantity of phosphorus flushed into the ocean was enormous, and the biological consequences were equally enormous. Cyanobacteria and eukaryotic algae, the photosynthetic organisms that had survived in scattered refugia through the glaciation, now found themselves in an ocean flooded with the one nutrient they needed most. They bloomed. Across the newly opened surface ocean, photosynthetic productivity surged to levels that had no precedent in the preceding Proterozoic. And every molecule of carbon dioxide fixed by photosynthesis, every organic molecule built from water and light and dissolved nutrients, produced a byproduct that would reshape the planet. Oxygen. This is the Neoproterozoic oxygenation event, a significant and sustained rise in atmospheric oxygen that followed the Marinoan glaciation. It was not the first time the Earth had experienced a jump in oxygen. The Great Oxidation Event, roughly 2.4 billion years ago, had lifted atmospheric oxygen from trace levels to perhaps a few % of modern concentrations. But for the entire Proterozoic, for over 1 billion years, oxygen levels had remained relatively stable and relatively low, perhaps 10 to 40% of present atmospheric levels. The boring billion had been boring in part because the oxygen concentration was too low to support large, metabolically demanding organisms and too stable to drive the kind of environmental disruption that forces evolutionary innovation. The snowball changed that. The nutrient flush from post-glacial weathering fueled photosynthetic blooms that pumped oxygen into the atmosphere faster than it could be consumed by chemical reactions or absorbed by reduced minerals in the ocean. Atmospheric oxygen concentrations climbed. The ocean itself began to oxygenate, not uniformly, not instantly, but progressively, as the photosynthetic surge overwhelmed the oxygen sinks that had kept the deep ocean anoxic for billions of years. But the story is not quite that simple. Work by Eric Sperling and colleagues, published in 2015 in Nature, used iron speciation data, measurements of the chemical forms of iron preserved in ancient marine sediments, to reconstruct the redox state of the oceans across this critical interval. What they found complicated the narrative in an important way. The oxygenation was not a clean, uniform transition from anoxic to oxygenated. It was patchy. Some ocean basins oxygenated rapidly. Others remained anoxic or became euxinic, rich in dissolved hydrogen sulfide, for millions of years after the glaciation ended. The picture was one of a planet in chemical transition, with oxygenated surface waters overlying deep waters that remained stubbornly anoxic in many regions. The oxygen was rising, but it was rising unevenly, creating a mosaic of chemical environments across the global ocean. This matters because it was precisely this mosaic, this patchwork of oxygenated and anoxic waters, of nutrient-rich and nutrient-poor zones, of chemically distinct habitats sitting side by side, that created the ecological opportunity for something entirely new. For 3 billion years, life on Earth had been overwhelmingly microbial. Single cells, mats, films, colonies at most. The energy available to individual organisms, the oxygen needed to sustain large body sizes and active metabolisms, and the ecological complexity required to drive evolutionary arms races had never been sufficient to push life beyond the microbial scale. The post-snowball world changed every one of those constraints simultaneously. More oxygen meant more energy. More nutrients meant more productivity. More environmental variability meant more ecological niches. and more niches meant more opportunity for organisms to diversify, specialise and compete. The stage was set. What walked onto it was unlike anything the planet had ever seen. The Ediacaran period takes its name from the Ediacara Hills in South Australia, where in the 1940s a geologist named Reginald Sprigg discovered strange impressions preserved in ancient sandstone. Disc-shaped forms, frond-like structures, and ribbed organisms unlike any known animal or plant. For decades, these fossils were treated with skepticism. They were too old, they were too strange. They did not fit neatly into any known category of life. But as similar fossils turned up on other continents, in Newfoundland, in Russia, in Namibia, in China, it became clear that the Ediacaran biota were not isolated curiosities. They were a global phenomenon, a new chapter in the history of life, written in the aftermath of the most extreme climate event the planet had ever endured. The Ediacaran period spans from approximately 635 million years ago, the termination of the Marinoan glaciation, to roughly 538 million years ago, the beginning of the Cambrian. It is the bridge between the microbial world and the animal world, and the organisms that inhabited it were extraordinary. At Mistaken Point, on the southeastern tip of Newfoundland, ancient seafloor surfaces preserve one of the oldest known assemblages of large, complex organisms on Earth. The fossils are impressions, not mineralized shells or bones, but the outlines of soft-bodied organisms pressed into volcanic ash that settled on the deep ocean floor roughly 565 million years ago. They are rangeomorphs, organisms built on a fractal branching architecture that has no parallel in the modern world. Each frond is composed of smaller units that replicate the structure of the whole, branching and sub-branching in a self-similar pattern that maximizes surface area relative to volume. They had no mouths, no guts, no obvious means of locomotion. They appear to have absorbed nutrients directly from the water through their enormous surface area. A feeding strategy so alien to modern animal life that for decades researchers debated whether rangeomorphs were animals at all, or something else entirely. Perhaps an extinct kingdom of life with no living descendants. Recent work has begun to resolve that question. Molecular clock analyses by Philip Donoghue and colleagues have shifted estimates of early animal divergence closer to the fossil record, placing rangeomorphs as possible stem group eumetazoans, organisms on the branch of the tree of life that leads to animals with true tissues, but sitting below the point where familiar animal body plans emerge. They were not quite animals in the way you would recognise, but they were on the road. In South China, the Dushantuo Formation preserves a different window into Ediacaran life, one measured in micrometers rather than centimetres. Exquisitely preserved microscopic fossils, including what appear to be embryonic cell stages of early multicellular organisms, have been recovered from phosphorite nodules roughly 600 million years old. These fossils are among the most debated in all of paleontology. Some researchers interpret them as early animal embryos, caught at the moment of cell division and mineralized before they could develop further. Others argue they are large, sulfur-oxidizing bacteria or algal spores. The debate continues, but the phosphorite deposits themselves are significant regardless of interpretation. They cluster in the post-glacial interval, formed from the very phosphorus flush that the snowball deglaciation delivered to the ocean. The chemistry that created the fossils and the chemistry that may have enabled the organisms to evolve in the first place are the same chemistry. And then there is Dickinsonia. Flat, oval, ribbed, and sometimes reaching over a metre in length, Dickinsonia is the iconic ediacaran organism, the poster child of the entire period. For decades, it was classified as everything from a jellyfish to a lichen to a giant protist. Its affinities were genuinely unknown. Then in 2018, a team led by Ilya Bobrovsky extracted organic molecules from exceptionally preserved Dickinsonia fossils found in the White Sea region of Russia. The molecules they found were cholesteroids, sterols that are produced exclusively by animals, not by bacteria, not by fungi, not by algae, by animals. Dickinsonia was an animal. The debate for this organism, at least, was settled by chemistry, the same discipline that had decoded the glaciations themselves. The ediacaran biota are strange, varied, and in many cases still poorly understood, but their significance is beyond question. They represent the first appearance of large, complex, multicellular organisms in the fossil record. They appear after the snowball. They appear in oceans that had been chemically remade by the most extreme glaciation-deglaciation cycle in Earth history. And they set the stage for what came next. An evolutionary explosion so rapid and so comprehensive that it redefined the meaning of biological complexity. Approximately 538 million years ago, the fossil record detonates. In a span of perhaps 15 to 25 million years, a sliver of geological time, nearly every major animal body plan that exists today appeared for the first time. Eyes, shells, articulated limbs, segmented bodies, digestive tracts with separate mouths and anuses, gills, claws, spines, predators and prey, locked in an arms race that drove innovation at a pace the planet had never seen and has never seen since. This is the Cambrian explosion, and it remains one of the most debated and most celebrated events in the entire history of life. The evidence comes from two extraordinary fossil windows. The Burgess Shale, in the Canadian Rockies of British Columbia, was discovered in 1909 and has yielded thousands of specimens of soft-bodied organisms preserved in exquisite detail. Animals with anatomies so bizarre that they defied classification for decades. Anomalocaris, a metre-long predator with a circular jaws and compound eyes containing 16,000 lenses. Hallucigenia, a worm-like creature walking on stilts with spines on its back, so strange that it was originally reconstructed upside down. Opabinia, with 5 eyes and a flexible frontal appendage that looks like nothing alive today. The Burgess Shale is a snapshot of a world in the grip of evolutionary experimentation. Organisms trying body plans that had never been tried before, and would in many cases never be tried again. The Chengjiang biota, in Yunnan province in southern China, provides a second window into the Cambrian explosion, slightly older than the Burgess Shale and equally spectacular. Preserved in fine mudstone roughly 518 million years ago, the Chengjiang fossils include some of the earliest known vertebrates, small, soft-bodied, fish-like creatures with notochords, the precursors to every animal with a backbone alive today. Your ancestors are in those rocks, tiny, eyeless, jawless, and unremarkable, but carrying in their body plan the potential that would eventually produce fish, amphibians, reptiles, mammals, and you. The hypothesized connection between Snowball Earth and the Cambrian explosion runs through oxygen. The post-glacial oxygenation event, driven by the phosphorus-fueled photosynthetic blooms that followed the Marinoan deglaciation, raised atmospheric oxygen past thresholds that larger, more metabolically demanding organisms required. In 2016, Xiaolin Zhang and Luo Kui published an analysis of the oxygen requirements of modern marine animals working backward from known hypoxic tolerances to estimate the minimum atmospheric oxygen concentration needed to support the body plans that appeared during the Cambrian. Their estimate placed the threshold at roughly 25% of present atmospheric levels, a concentration that the Neoproterozoic oxygenation event appears to have reached in the tens of millions of years following the Marinoan. Sperling and his colleagues extended this analysis further, showing that the sequence in which animal phyla appeared in the fossil record correlated with their oxygen sensitivity. The first animals to appear, sponges and other simple body plans, are the most tolerant of low oxygen. Later arrivals, arthropods, mollusks, chordates, require progressively more. The fossil record reads like a waiting list, ordered by how much oxygen each group needed to function. As the atmosphere climbed, new body plans became viable, and the fossil record expanded accordingly. But honesty demands a caveat. The Marinoan glaciation ended 635 million years ago. The Cambrian explosion began roughly 538 million years ago. That is a gap of nearly 100 million years. A century of millions of years separates the end of the ice from the onset of the evolutionary explosion. Direct causation, the idea that the snowball directly triggered the Cambrian explosion, is difficult to sustain across such a gap. What the evidence supports is a chain of consequences, not a single cause. The snowball created the conditions, oxygen, nutrients, ecological disruption, that made complex animal life possible. But translating that possibility into reality took time. Molecular clock estimates suggest that the major animal lineages began diverging during or shortly after the Cryogenian. But the diversification into the body plans preserved in the Burgess Shale and Chengjiang took tens of millions of years of additional evolution, ecological interaction, and environmental change. There is also the concept of ecological cascading, the idea that once environmental conditions crossed the threshold for complex animal life, biological feedbacks accelerated the process. Predation drives the evolution of defences. Defences drive the evolution of new predatory strategies. Organisms that engineer their environment, burrowing into sediment, building reefs, filtering water, create new habitats that other organisms can exploit. Each innovation opens a door that enables the next. The ecological snowball, as some researchers have called it, may have been as important as the geological one. A self-reinforcing cascade of biological innovation that, once started, could not be stopped. The Cambrian explosion was not caused by Snowball Earth in the way that a match causes a fire. It was caused by a sequence of events that began with the snowball and unfolded over 100 million years of chemical, ecological, and evolutionary change. The ice created the conditions. The chemistry enabled the biology. And the biology, once unleashed, transformed the planet in ways that are still visible in every living organism on Earth today, including the one listening to this story. Every body plan you carry, your bilateral symmetry, your segmented spine, your nervous system, your eyes, has its origin in the Cambrian, and the Cambrian has its origin in the oxygenation that followed the snowball, and the snowball has its origin in the breakup of Rodinia, the weathering of tropical basalts, and the ice albedo feedback that froze the planet from pole to pole. Pull on one thread, and the entire tapestry unravels back to a frozen world 700 million years in the past. The catastrophe did not merely test life, it remade it. The question that remains is whether the catastrophe could ever return. So could it happen again? Could the ice return, not as a polar cap, not as a glacial advance, but as a planetary seizure, a freeze that swallows the equator and seals the oceans and silences the surface of the Earth for millions of years. You have now heard the full story of what it took to freeze this planet. You know the mechanism. You know the evidence. You know what survived and what emerged on the other side. The question of recurrence is not hypothetical. It is a question about the physics of the world you are standing on right now. Whether the conditions that produced the most extreme climate event in Earth history could ever align again. Start with the Sun. 700 million years ago, the Sun was approximately 6% dimmer than it is today. That may sound like a small number. It is not. 6% less solar energy reaching the Earth's surface meant the entire climate system was operating closer to the freezing threshold. The margin between a stable, warm planet and a runaway ice albedo feedback was thinner. Less forcing was needed to push the system over the edge. Today, the Sun is brighter. It delivers more energy per square metre to the Earth's surface than it did during the Cryogenian. That additional energy raises the temperature at which the ice albedo feedback could become self-sustaining, making it harder, significantly harder, for ice to advance far enough from the poles to cross the critical latitude. The threshold that Boudica identified still exists in the physics. It has not gone away. But the Sun has moved the planet further from it. Now consider the continents. During the Neoproterozoic, Rodinia straddled the equator. The tropics, where rainfall is heaviest, where temperatures are highest, where chemical weathering of rock is fastest, were covered in continental crust. Every rainstorm that fell on that equatorial landmass dissolved carbon dioxide from the atmosphere and locked it into the ground. The geography was a carbon dioxide pump, pulling greenhouse gas out of the air with maximum efficiency. Today, the continental configuration is different. Major land masses sit at mid and high latitudes: North America, Europe, Asia, Antarctica. The tropics are dominated by ocean, with relatively little exposed continental rock in the equatorial belt. Weathering still occurs, but it occurs more slowly, at higher latitudes, where temperatures are lower and chemical reactions are less efficient. The carbon dioxide drawdown that helped trigger the Neoproterozoic snowball would be far more difficult to replicate with the modern arrangement of continents. And then there is the atmosphere itself. The direction of travel today is not toward less carbon dioxide, it is toward more. Human activity has raised atmospheric carbon dioxide concentrations to levels not seen in at least 3 million years, and the trajectory is still climbing. The planet is warming, not cooling. Ice sheets are retreating, not advancing. The Arctic is losing ice cover at rates that can be measured in decades, not millennia. The modern climate crisis is, in almost every respect, the opposite of the Snowball Earth scenario. Too much greenhouse gas, not too little. The idea that the planet might stumble into a global glaciation while atmospheric carbon dioxide sits at over 400 parts per million is not merely unlikely. It is physically incoherent. The greenhouse effect that carbon dioxide provides is the single most effective barrier against the ice albedo feedback, and humanity is currently reinforcing that barrier at an unprecedented rate. So, on every count, solar luminosity, continental geography, atmospheric composition, the conditions that produced Snowball Earth are absent from the modern world. The specific conspiracy of forces that froze the planet 700 million years ago cannot reassemble under current conditions. The sun is too bright. The continents are in the wrong place. The atmosphere carries too much carbon dioxide. A Snowball Earth is not coming back. Not in our lifetime. Not in the lifetime of our species. not in any time frame that human civilization could meaningfully prepare for or respond to. But zoom out further, much further. On timescales of hundreds of millions of years, the sun continues to brighten. It has been doing so since it first ignited 4.5 billion years ago, and it will continue to do so for another 5 billion years until it exhausts its hydrogen fuel and expands into a red giant. As the sun brightens, the Earth's climate system must compensate. The silicate weathering cycle, the same thermostat that broke during the snowball, responds to increasing solar energy by pulling more carbon dioxide from the atmosphere, cooling the surface to maintain equilibrium. Weathering speeds up. Carbon dioxide concentrations drop. The greenhouse effect weakens just enough to offset the rising solar input. This works for a while, but it has a limit. In roughly 500 million to a billion years, depending on the model, the weathering cycle will have drawn atmospheric carbon dioxide down to concentrations so low that photosynthesis can no longer function. Plants will die. The oxygen they produce will stop being replenished. The biosphere that depends on them will collapse, not from a catastrophe, but from a slow, inexorable chemical strangulation. The planet will not freeze. It will overheat. The brightening sun will eventually push surface temperatures beyond the point where liquid water can exist, and the Earth will enter a runaway greenhouse, the opposite of the snowball, and equally fatal. Caldera and Casting mapped this trajectory in their work on the long-term carbon cycle. The habitable window, the period during which this planet can sustain liquid water and a functioning biosphere, is not infinite. It had a beginning, and it will have an end. The Snowball Earth sits near one edge of that window, when the sun was faint and the climate was fragile enough to tip into a frozen state. The future end sits at the other edge, when the sun will be too bright and the climate too hot for life as we know it. Between those two extremes lies the narrow corridor of time during which this planet is habitable, and we are somewhere in the middle of it, looking back at the ice and forward at the fire. Here is what Snowball Earth teaches you, if you are willing to sit with it. This planet is not stable. It feels stable. It feels permanent. The oceans seem eternal, the continents immovable, the climate a fixed backdrop against which human history unfolds. But the geological record tells a different story. It tells you that the same planet you are sitting on right now once froze from pole to pole. That ice a kilometre thick covered the ocean at the equator. That photosynthesis shut down for 50 million years. That the chemistry of the entire ocean was rewritten by the absence of light. And it tells you that the planet recovered. Not gently, not gracefully, but completely. Life survived in cracks and vents and dirty pools on the surface of glaciers. And when the ice broke, it exploded into forms that had never existed before. Forms that eventually, through a chain of consequences spanning hundreds of millions of years, produced you. The climate system is not a wall. It is a wire. It holds weight, it carries tension, and under the right conditions, it can carry the extraordinary cargo of a living, breathing, thinking biosphere across billions of years. But push it hard enough, in either direction, and it will snap. It has snapped before. It snapped 700 million years ago, when a conspiracy of dim sunlight, equatorial rock, and vanishing carbon dioxide sent the planet into the longest winter it has ever known. And what brought it back was not intelligence, not intervention, not design. It was a molecule. A colourless, odourless gas seeping from volcanoes into a sky that had no way to clean it, building for millions of years until the physics had no choice but to relent. Carbon dioxide froze this planet. Carbon dioxide saved it. And right now, on the only world in the known universe where anything is alive to notice, that same molecule is accumulating in the atmosphere faster than at any point in the last 66 million years. The direction is different. The stakes are the same. The wire is the same wire. And it does not care which direction you push